The definition of a prime number is any positive integer which can be divided by 1 and the number itself only. And we exclude number 1 from the set of prime numbers. So 1 is looks like it can be divided by only 1 and itself, but we are not including that one as a prime number. So starting from number 2, the only divisor is 1 and 2 itself. Of course, when you're talking about the prime numbers, we are not thinking about negative factors. So it has only 1 and itself. So it should be uh, prime number. Then the electrostatic method is when you choose that prime number, then the multiples of that number is not going to be a prime number because, for example, like 12 is a multiple of 2, then 12, any integer is actually has 1 and itself as its uh, divisors, right? So it has something else like 2, 3, 4, 5. Then it doesn't satisfy the prime number definition, right? So because of that, whenever we find out one prime numbers, and automatically the multiple of that number cannot be the prime number. Okay? So this method gives us a certain way to find those prime numbers. So let's say between 1 and 100, we found the 2 is the prime number, and after deleting all these multiple of 2's, the smallest kind of number after 2, which is still survived from that cancellation, should be the next prime number. 3, yes. Then after 3, we have to delete the multiple of 3. Now, 6 is a multiple of 3 too, but it was already cancelled out by multiple of 2. But 9, we have to cancel out that. 12, like that. And 15, and 21, right? So we just do these procedures. So after we finish all these procedures, the survived ones are the only prime numbers between 1 and 100. Okay, you can download this Excel file from course Blackboard in this chapter. So using this one, let me just show you how it's going to work. So let's say between 1 and 100, I'm looking for prime numbers. And it shows these are the survived ones. So let's just look at one by one for each step. So first, let's choose number 2. That's the survived one so far. Then we just delete all these multiple of 2's from the list. Okay, then the next survived one is number 3, then 3. So let's type in 3 and hit enter. And these are the new numbers, which is multiple of 3. So it's just cancelled out by that. Okay, the next survived number is 5. So click step and type in 5 and click OK. And these are the new numbers, which are the multiple of 5's. So next one is 7. So type in 7 and click OK. And we have only few deleted by that. Now, the question is, how far do we have to do this? Which means, okay, after 7, then the next one is 11. Okay, so let's just try it. And you see there's a pink over there. So what's the meaning of this one? So, but let's just keep doing this one. So next step, the next survived one is 11, which should be a prime number. So let's just looking for the multiple of primes in this list. When you click it, there is no yellow number appears, which means what? Among these survived ones, after finishing multiple of 7s, there is nothing is multiple of 11 anymore. Okay, let's check one more. 13, how about multiple of 13s? Yes, it looks like there is no more. So which means after 11, all these numbers are actually prime numbers. So it's kind of the relatively simple procedures. It doesn't take that long, right, to find all the prime numbers up to 100. all we need is just checking 2, 3, 5, 7. The multiple of those four numbers are enough to find those holding. Cool, right? It's really great. And there must be some reason for this red, okay? The pink number, which is kind of uh, 10 in the beginning. So why it's so important, okay? So let's just check something else. Instead of 100, let's change some number. So how about 1 through 300? Let's say 400, okay? Then these are the results, all the survived ones, up to 400. Okay, then let's just check one by one, step by step. So first, it should be 2. Click OK. Then these are the multiple of 2's. So we found those results. Okay, good. Then go to the next one, is 3. Then these are multiple of 3's. Okay, so we cancel out. Then now, when you look at it, this pink number is not 10 anymore. It goes to 20. Okay, so let's just keep doing it. How about 5? Then we know we should have some numbers are deleted as the multiple of 5, right? So we should guarantee up to 7 because we already checked that in the previous cases, right? Okay, so then how about 11? Then yes, there are some numbers are still survived after deleting multiple of 7, right? And these numbers are multiple of 11, so it's cancelled out at this moment. Now let's look at this case. 11 is less than 20, and the meaning is we still have some numbers are multiple of 11. Then how about 13, which is less than 20 in this case? Okay, maybe, yeah, but still there is some numbers that cancel out. So next one is 17. And yes, it's only 3, but those are multiple of 17s. Okay, 19 is still less than 20, so let's find out the multiple of 19s among the survived ones. And it looks like there is 1. Okay, then after that, if you choose the next prime number, which is 23, there's no number, looks like it's a multiple of 23. And the 23 itself is greater than 20. So there must be a relation, right? If you're looking for prime numbers between 1 and 100, the numbers we need to check for the multiples of them are up to just 10, right? But if it's a 1 through 400, then the numbers we need to check for the multiples of them is up to 19, which is less than 20, right? So if the maximum number that we want to check the prime is 100, then we need to check up to 10. If it's a 400, then we need to check up to 20. Can you see the relations of them? So how about the I think 625 is, let me check, divided by 25 is 25, right? So 625 is 25 squared. So let's do that one more time to check it. So how about up to 625? So looking for prime numbers up to 625. And these are the results. And can you see that? This pink number is 25, right? So if it's a 100, it's up to 100, then we need to check up to 10. If it's a 400, then we need to check up to 20. And if it's a 625, then we should check just up to 25. So it looks like we need to only check square root of the maximum given number, okay, to find this one. So that's the procedure of these electrochemical procedures. Okay, and we are going to check why we need to check. It's only necessary to check up to square root of n. Okay, to find the prime numbers a little bit later. But okay, so you can just use this Excel file to check those steps. Okay. So that's the Eratosthenes procedures. Okay, and from there we should have some prime numbers. Okay. You can find them like that. So using this Excel file, the primes, you can just find out primes, and these are the prime numbers, and these the orders of the prime numbers. So 11's prime number is 31, okay, like that. So up to 100, we have total 25 prime numbers there. And the next one actually shows just what prime numbers, like. So these are the 1 through 100, for example, and these are the orders of prime numbers like that. So you can change this one to any number. Just be careful not too big number. Okay, so up to 2345, then these are the list. So there are total 347 prime numbers up to that. Okay? And this one actually shows those positions of those. And the third tab actually is already built in. So up to 60,000, we have 6,057 prime numbers. And you know what? The last prime number up to that much is 59,999. So this is a prime number. Okay? So this one is just fixed one, no matter what. Okay, so you can just check up to that much, the prime numbers for that much. But these two tabs, starting from the main ones and give some number, then you will get all the prime numbers up to that. Okay. Okay, next one, we are not going to prove it, but this is very important one. The every integer n greater than 1 can be expressed as a product of prime numbers and uniquely. Okay, so this is the power of the theorem. Okay? And because of this, instead of dealing with the big number, actually we could dissect this big number into the collection of much smaller numbers. So we could handle this big number in much easier way. And the way of dissecting is unique. That's the meaning of it. So no matter what number you're dealing with, and whoever try to take the dissect of it, if it's a prime factorization, then it's unique for that. So we could building up some kind of theory and some type of rules, something like that, right? And the huge part of math is based on this fact: number theory, cryptography. Right? So nowadays, the secrecy is the everything, right? And these codings and make the password and all the stuff, right? Is based on the powers of prime. And why this prime is so powerful? The big portion of the reason is because we have the unique factorization of any integer. So please remember just that one here. And let's try to prove this. And this one explains why we need to check up to just the square root of n using that Eratosthenes method to find the prime numbers. This statement says for every composite number n has a prime factor which is less than equal to square root of n. Okay, so composite number means what? It's not prime number. And that means that number can be written by, of course, one way is 1 times n, always. So prime number, composite number, doesn't matter. Any integer can be written by 1 times n. But if it's a prime number, then that's the only factorization, right? 1 and n, that's it. But if it's a composite number, means there is at least another prime factor. Let's say it's a. Then it's a factor, which means divisor. There must be a quotient, right? Without remainder, or remainder is 0. So that composite number can be written by a times b, which will be factors of n, or divisor of n, okay, automatically. Then it says at least one of them, a or b, doesn't matter, must be less than equal to square root of n. So let's just prove it. So let's do any arbitrary integer is a composite number. Of course, in natural number set, right? Right now we're talking about just positive integers right now. And then n can be written by a times b, right? And this a, b's are just some integers, or positive, of course, a and b, but they have certain properties, right? So it's like this. We already know any integer can be written by 1 times n, which is not interesting. We are not interested about it because we are dealing with some non-prime number cases. So a, b, we don't want to accept the possibility to become 1, right? So a or b should be greater than 1. And maybe a, b's are same numbers, but most likely they are different numbers. So without loss of any generality, we can say a is less than equal to b, right? They could be equal, but in that order. And definitely, because a, the smaller number is greater than 1, so the larger number is less than n itself, right? So this ab must satisfy in that condition. Then from this, when you multiply a on both sides, a is a positive, so we just keep the inequality, then we still have this inequality, but a times b was n, so we can have n over there. So which means a squared is less than equal to n, right? So when you take square root of on both sides, we are going to have a is less than equal to square root of n. Okay, so we have a is greater than 1. Then by the fundamental theorem of arithmetic, the previous theorem says a has at least one prime factor, right? Because any number, any integer other than 1 has a unique prime factorization, right? So it has at least one prime factor. So say p. Okay? Then clearly, because p is a factor or divisor of a, therefore p must be less than equal to a. Sometimes a is that prime factor, who knows? And that is less than equal to square root of n, right? Because of that. So we had p is a factor of a, divisor of a, and we already have a itself is a divisor of n, right? So because of this, p should be a divisor of n itself, right? So we just to show that there is a prime number which is a divisor of n, and that is less than equal to square root of it. So this one is the end of proof for entire one. But more important thing from this theorem is we wonder how many primes, or looking for the primes 1 through 100, for example, right? So if you choose any number here, so then n is less than equal to 100 and looking for that number. And by this theorem, there is a prime number which is less than equal to square root of n. So when you try to looking for what is the square root of 100, it's 10. Then no matter which n we choose, which is smaller than 100, that number should have a prime number which is less than equal to square root of 100, technically, right? So that's the reason why it's enough to check any prime which is less than equal to square root of that largest number, the boundary numbers of this group. And any survived number after deleting the multiple of those numbers should be prime number. Because if this one cannot kind of divide any of these further survived ones anymore. Okay? If any number is multiple of that, then it should be multiple of n is to one of these already, okay, by this theorem. Okay, so that's why in that Eratosthenes method, all we need is whenever we're asking 1 through 400, then we are looking for just multiple of square root of 400, which is 20, right? So just looking for those numbers up to 20. So that procedure is quite simpler than we think.